Good morning, everyone. Today I, Yamni, a student of Chemistry Honors, second year, is here to read chapter Colloidal State of Matter of Physical Chemistry. So, Thomas Graham, 1861, studied the rate of diffusion of liquids and solutions across the animal membranes, and as a result of his experiments, he divided the soluble substances into two classes: first, crystalloids, and second, colloids. The substances like common salt, sugar, urea, etc., which can be obtained in the crystalline form and in the dissolved state diffused through the vegetable or animal membrane, were termed as crystalloids, and the substances like starch, gum, glue, etc., which are non crystalline in nature and in the dissolved state do not diffuse or have a little tendency to pass through the animal or vegetable membrane, were given the name colloids. Graham's classification of substances into crystalloids and colloids were soon proved to be wrong. A crystalloid was found to behave as a colloid under different set of conditions and vice versa. For example, sodium chloride behaves as crystalloid when dissolved in water but behaves as a colloid when dispersed in benzene. It has since then been realized that a clear cut difference do not exist between crystalloids and colloids. The non diffusibility of colloids and diffusibility of crystalloids through the animal or vegetable membrane was shown to be due to the difference in size of particles of crystalloids and colloids. The colloids from bigger particles which cannot pass through the membrane. It is therefore preferable to speak of a substance in colloidal state rather than calling it a crystalloid or a colloid. The particle size limits are given below. So we have true solutions, colloidal solutions, and suspensions. In true solution, size is less than 10 raised to power minus 9 or 1 nanometer. In colloidal solution, between 10 raised to power uh, minus 9 and 10 raised to power minus 7 or 1 nanometer to 100 nanometer, and in suspensions more than 10 raised to power minus 7 or 100 nanometer. Thus, the size of the colloidal particles is intermediate between that of particles of true solution and those of suspensions. Now, our next topic is a, colli- a colloidal state of matter is therefore a state in which the size of the particle is such 10 angstrom to 1000 angstrom that they can pass through filter paper but not through animal or vegetable membrane. Thus, every substance can be brought into colloidal state by adopting suitable methods. They distinguish between characteristics of true solutions, colloidal solutions, and suspension is given in table 7.1. So it uh, characteristics of true solutions, colloidal solutions, and suspensions. First, the differentiation is on base of particle size. So true solution have size less than 10 raised to power minus 9 m or 1 nanometer, that is less than 10 angstrom. Then in colloidal solution size is between 10 raised to power minus 9 to 10 raised to power minus 7 m or 1 nanometer to 100 nanometer, that is 10 angstrom to 1000 angstrom. And in suspension, the size is more than 10 raised to power minus 7 m or 100 nanometer, that is more than 1000 angstrom. Now, on the basis of filterability, true solutions pass through ordinary filter paper as well as animal membrane, while colloidal solution pass through ordinary filter paper but not through animal membrane, and suspensions do not pass through filter paper and animal membrane. Then, on the basis of settling, so true solution do not settle, colloidal solution also do not settle, and suspension settle on standing. On the basis of visibility, particles are invisible in true solutions. In colloidal solutions, scattering of light by particle is observed under ultra microscope. Then in suspensions, particles are visible to naked eye or under a microscope. On the basis of diffusion, true solution diffuse quickly, colloidal solution diffuse slowly, suspensions do not diffuse. Now our last is on the basis of appearance. Then true solutions are clear and transparent, colloidal solutions translucent, and suspensions opaque. A simple example to understand a true solution, a suspension, and a colloidal solution is to consider the solution of sugar in water and that of water in which mud is stirred. The former is a true solution, but in case of the latter, so long as the steering is continued, the mud remains in suspension, but as soon as steering is stopped, the larger particles fall to the bottom of the vessel. However, smaller particles remain in suspension for longer time, say for several days. Then this part of water containing minute mud particles which cannot be seen even under a microscope and pass through the filter paper is a colloidal solution. Now coming to our next topic, types of colloidal system. So, just as in true solution, the substance dissolved is called the solute, and the medium in which it is dissolved is called the solvent. Similarly, in the colloidal system, the terms solute and solvent are replaced by the terms dispersed phase and dispersion medium, respectively. Thus, dispersed phase means the substance distributed in the dispersion medium in the form of colloidal particles, and the dispersion medium means the medium in which the substance is dispersed in the form of colloidal particles. The colloidal system thus obtained is sometimes called a colloidal dispersion or a dispersed system. Evidently, unlike a true solution which is homogeneous, a colloidal system is heterogeneous, consisting of two phases, the dispersed phase and the dispersion medium. Depending upon whether the dispersed phase and the dispersion medium are solid, liquid, or gases, eight types of colloidal systems are possible. A gas mixed with another gas forms a homogeneous mixture and not a colloidal system. The examples of the various types, along with their typical names, are listed in Table 7.2. So, in if the dispersed phase is solid, dispersion medium is solid, solid salt. Example, some colored glasses. Then if solid is dispersed phase, dispersion medium is liquid, then name will be salt. Some example will be some paints, muddy water. Then if dispersed phase is solid, dispersion medium is gas, name is acrosol. Example is smoke and dust. Then our fourth is if dispersed phase is liquid, dispersion medium is solid, then name will be gel. Example will be cheese, butter, jellies. If dispersed phase is liquid, dispersion medium is also liquid, then name will be emulsions, and example will be milk, hair cream. Then if dispersed phase is liquid, dispersion medium is gas, then name will be aerosol, and example will be fog, mist, cloud. If dispersed phase is gas, dispersion medium is liquid, name will be foam, examples will be froth, whipped cream. Out of the various types of colloidal system listed in table 7.2, the most common are solids in liquids, then in gels. Second one is gels, liquids in solid, and then is emulsions, liquid in liquids. Further, it may be mentioned that depending upon the dispersion medium, the salts are given special names as follows. Dispersion medium is water, the name of the salt, aquasol or hydrosol. Dispersion medium is if alcohol, then name of the salt alcohol. If dispersion medium is benzene, then name of the salt benzosol, and dispersion medium is gases, then name of the salt is aerosol. Now our next topic, classification of colloids or colloidal salts. The various substances which form colloidal salts are divided into two categories, namely leophilic and leophobic. If water is a dispersion medium, the term used are hydrophilic and hydrophobic. Now, our first is leophilic colloids. So, the word leophilic means liquid loving substances like gum, gelatin, starch, rubber, etc., which, when mixed with a suitable liquid as a dispersion medium, directly form the colloidal salts are called leophilic, and the salts thus obtained are called leophilic salts. As they form the colloidal salts directly, they are called intrinsic colloids. An important characteristic of these salts is that if the dispersed phase is separated from the dispersion medium, say by evaporation, the salts can be made again by simply remixing with the dispersion medium. That is why these salts are called reversible salts. Further, these salts are quite stable and cannot be easily precipitated. Now, our next topic is leophobic colloids. The word leophobic means liquid hating. Substances like metals, their sulfides, etc., when simply mixed with the dispersion medium, do not form the colloidal salts. Their colloidal salts can be prepared only by special methods, as discussed later. Such substances are called leophobic, and the salts formed by them are called leophobic salts. As their colloidal salts have to be prepared by indirect methods, they are also called extrinsic colloids. These salts are readily precipitated or coagulated and hence are not stable. Further, once precipitated, they do not give back the colloidal salts by simply addition of the dispersion medium. Hence, these salts are also called irreversible salts. The greater stability of the leophilic colloidal salts than the leophobic colloidal salts is due to the fact that the former are highly hydrated in the solution. The essential points of difference between the leophilic salts and leophobic salts are given in table 7.3. So, now points of differences between leophilic and leophobic salts. Property, on the basis of ease of preparation. So, leophilic salts prepared easily by directly mixing when the liquid with the liquid dispersion medium, and leophobic salts cannot be prepared directly, prepared by special methods only. On the basis, second is on the basis of stability. They are quite stable and are not easily precipitated or coagulated. Leophobic salts, they are easily precipitated by addition of a small amount of a suitable electrolyte. Our third property is on the basis of hydration. So leophilic salts are highly hydrated and leophobic salts are not much hydrated. Next is on the basis of reversible and irreversible nature. Leophilic salts, they are reversible in nature. That is, once precipitated, can reform the colloidal salts by simply mixing with the dispersion medium. And leophobic salts are irreversible in nature. That is, once precipitated, cannot form the colloidal salts by simple addition of the dispersion mediums. Now, next is our nature of on the basis of nature of substances. So, leophilic salts are usually formed by the organic substances like starch, gum, proteins, etc. And leophobic salts are usually formed by the inorganic materials like metals, their sulfides, etc. Now, next is on the basis of viscosity. Their viscosity is much higher than that of the medium, and leophobic salts' viscosity is almost the same as that of the medium. Now, on the basis of surface tension, their surface tension is usually lower than that of the dispersion medium, and in leophobic, their surface tension is nearly same as that of the dispersion medium. Our next property is on the basis of visibility. So, leophilic salts particles are neither visible nor detected easily by the ultra microscope by the scattering of light. Then in leophobic salt, their particles, though not visible, can be easily detected by an ultra microscope. Then our last property is on the basis of migration in an electric field. Their particles may migrate in either direction or may not migrate at all. And leophobic salts particles migrate in only one particular direction in the electric field. Our next topic is multimolecular, macromolecular, and associated colloids. The main characteristic of a colloid is its particle size. When some solid substance is dispersed into a medium in which the solid substance is otherwise insoluble, such that after dispersion the size of the solid particles lies in the colloidal range, the system is called a colloidal dispersion. Example of colloidal dispersion are gold sol, a colloidal dispersion of As2S3 in water, etc. Depending upon how the different substances may have size in the range of the colloids, the various type of colloids or colloidal dispersions may be divided into the following three categories: multimolecular colloids, macromolecular colloids, and our third one is associated colloids. So, multimolecular colloids. When on dissolution, a large number of atoms or smaller molecules of a substance with diameter less than 1 nanometer aggregate together to form species having size in the colloidal range. The species thus formed are called multimolecular colloids. The dispersed phase in this type of colloidal system may contain large aggregates of atoms or molecules formed as a result of aggregating properties of the dispersed particles. For example, a gold sol may contain particles of various sizes having several atoms. Sulfur sols consist of particles containing 1,000 or so of S8 sulfur molecules. These are held together by van der Waals forces. Now, our second is macromolecular colloids. When certain substances having a big size molecules called macromolecules having large molecular masses are dissolved in suitable liquid, they form a solution in which the molecules of the substance, that is, the dispersed particles, have size in the colloidal range. Such substances are called macromolecular colloids. These macromolecular substances are usually polymers with very high molecular masses. Example of naturally occurring macromolecules are starch, cellulose, proteins, enzymes, and gelatin. Examples of man-made macromolecules are po- uh, polyethylene, nylon, polystyrene, synthetic rubber, etc. As these molecules have large sizes and have dimensions comparable to those of colloidal particles, their dispersions are called macromolecular colloids. Their colloidal solutions are quite stable and resemble true solutions in many respects. Now, our third one is associated colloids. The substances which, when dissolved in a medium at low concentration, behave as normal strong electrolytes but at higher concentration exhibit colloidal state properties due to the formation of aggregate particles are called associated colloids. The aggregated particles thus formed are called micelles. The formation of micelles take place only above a particular temperature called Kraft temperature Tk and above a particular concentration called critical missile concentration CMC. The most common example of associated colloids is that of surface active agents such as soaps and synthetic detergents. For soap, the CMC is 10 raised to power minus 4 minus 10 raised to power minus 3 mole per liter. Each missile contains at least 100 molecules. Now, mechanism of micelle formation. Let us take the example of soap solutions. Soap is sodium salt of higher fatty acid and may be represented as RCOONA. Example, sodium stearate with CH3 CH2 power 16 COO negative Na positive. When dissolved in water, it dissociates into RCOO negative and Na positive ions. The RCOO negative ions, however, consist of two parts, that is, non-polar long hydrocarbon chain R called the tail, which is hydrophobic, that is water repelling, and the polar group COO negative called the head, which is hydrophilic, that is water loving. The RCOO negative ions are therefore present on the surface with their COO negative groups in water, and the hydrocarbon chain are staying away from it and remain at the surface. However, at higher concentration, these ions do not remain on the surface but are pulled into the bulk of the solution. As a result, at higher concentration, the RCOO negative ions form an oily aggregate with their hydrocarbon chains represented by wavy lines pointing towards the center and the COO negative part represented by the solid circle outwards as shown above. An aggregate thus formed is known as ionic micelle. Each of these micelle may contain up to 100 ions. Similarly, in case of detergents, example sodium lauryl sulfate with CH3 CH211 SO4 negative Na positive. The polar group is SO4 2 negative along with the long hydrocarbon chain. Hence, the mechanism of micelle formation is similar to that of soaps. It is interesting to add here that at CMC, missiles are almost spherical at concentration slightly higher than but close to CMC. They form flattened spheres. At still higher concentrations, they form extended parallel sheets 2 molecules thick. These are called lamellar missiles. It was shown for the first time by MC Bain in 1913 by X-ray analysis the existence of plate-like missile of soaps, hence they are named as MC Bain missiles. The comparison of the main characteristics of the above three types of colloids is given in table 7.4. If stearic acid or palmitic acid is taken, the RCOO negative ion will stay on the surface only. Now, in table 7.4, comparison is given between multimolecular colloids, macromolecular colloids, and associated colloids. So, multimolecular colloids are formed by the aggregation of a large number of atoms or molecules will generally have diameter less than 1 nanometer, example salts of gold, sulfur, etc. Macromolecular colloids, they are molecules of large size, example starch, proteins, and polymers like rubber, nylon, etc. Associated colloids are formed by aggregation of a large number of ions in concentrated solution, example soap salt. Second, on the basis of their molecular masses. Multimolecular colloids have not very high molecular masses. Macromolecular colloids have high molecular masses. Associated colloids molecular masses are generally high. Now, about on the basis of forces, in multimolecular colloids, atoms or molecules are held together by weak van der Waals forces. In macromolecular collide, they are due to long chain, the van der Waals forces holding them are comparatively stronger. And in associated collides, higher is the concentration, greater are the van der Waals forces. Now, on the basis of their character, multimolecular colloids have usually lyophilic character, macromolecular colloids have lyophilic character, and associated colloids contain both lyophilic and lyophilic groups. Our next topic is preparation of colloidal solutions. As discussed earlier, the lyophilic salts can be prepared directly by mixing the substance with the dispersion medium. For example, colloidal salts of starch, gelatin, gum, arabic, soaps, etc. are prepared by simply dissolving these substances in warm water. Similarly, a colloidal salt of cellulose nitrate is obtained by dissolving it in an organic solvent such as ethyl alcohol. The product obtained is called collodion. However, the lyophilic salts cannot be prepared directly. Hence, the following two types of methods are employed for obtaining the lyophilic salts. First is dispersion or disintegration methods. These methods involve the breaking of the bigger particles to colloidal size. The methods generally employed for this purpose are briefly described below. We Dispersion or disintegration method can be done by three ways: mechanical disintegration, second is electro disintegration, and third is peptidization. So, first one is mechanical disintegration. The mechanical disintegration is carried out in the machine called colloid mill. It consists of two steel discs with a little gap in between and capable of rotating the opposite directions at high speed. A suspension of the substance in water is introduced into the mill. The size of suspension particle is reduced to that of colloidal size. We can see its diagram in figure number 7.2. Now, our next is electro disintegration, Bredik's method. This method is employed for obtaining colloidal solution of metals like gold, silver, platinum, etc. An electric arc is set up between two metallic electrodes suspended in a trough of water. The intense heat of the arc converts the metal into vapor, which are condensed immediately in the ice cold water bath, resulting in the formation of particles of colloidal size. We can see its figure in 7.2, 7.3, Braddock's method. Now, our third one is peptization. Peptization is a process of passing of a precipitate into colloidal particles on adding suitable electrolyte. The electrolyte added is called peptizing agent. A few examples of salts obtained by peptization are given below. A reddish brown colored colloidal solution is obtained by adding small quantity of ferric chloride solution to the freshly precipitated ferric hydroxide. Our second one is a precipitate of silver iodide can be peptized by shaking with a dilute solution of silver nitrate of Ki. Third, on adding insufficient quantity of very dilute HCl solution to the freshly precipitated aluminium hydroxide, a sol of aluminium hydroxide is obtained. We can see its figure 7.4, preparation of colloidal solution by peptization. Now, cause of peptization. As the electrolyte is added to a freshly precipitated substance, the particles of the precipitated preferentially absorb one particular type of ions of the electrolyte and get dispersed due to electrostatic repulsions. This gives particles of a colloidal size. Freshly prepared precipitates are preferred as they are easily peptized. Now, second one is condensation or aggregation methods. These methods involve the joining together of a large number of smaller particles to form particles of colloidal size. The methods generally employed for this purpose are as follow. First one is by chemical reactions. So in this we can do by double decomposition, by reduction, then by oxidation, and fourth is by hydrolysis. And so by double decomposition, when H2S is passed through a dilute solution of arsenious oxide in water, a colloidal solution of arsenious sulfide is obtained. As we can see here, As2O3, which is our arsenious oxide, when is passed through H2S, 3H2S give As2S3 plus 3H2O. As2S3 is our colloidal solution. Then second is by reduction. Gold, silver, platinum, etc. are obtained in colloidal form by reduction of very dilute solutions of their salts with a suitable reducing agents. Gold sol can also be obtained by reduction of AuCl3 solution with formaldehyde and tannic acid or with hydrazine. Third one is by oxidation. Then sulfur is obtained in the colloidal form when H2S is bubbled through the solution of an oxidizing agent like nitric acid, bromine water, etc. Fourth one is by hydrolysis. Then FeOH3 and AlOH3 salts are obtained by boiling solution of their corresponding chlorides. FeCl3 plus 3H2O gives FeOH3 plus 3HCl. Now, second, by exchange of solvent, substances like sulfur and phosphorus are fairly soluble in alcohol but less soluble in water. If their alcoholic solutions are poured in water, colloidal solutions of sulfur and phosphorus are obtained. Third one is by condensing vapors of a substance into the solvent. Colloidal solutions of sulfur and mercury in water are prepared by passing their vapors in cold water containing a little stabilizing agent like ammonium nitrate. Fourth one is by excessive cooling. Colloidal solution of ice in an organic solvent like ether is obtained by freezing a mixture of the solvent and water. Now our next topic is purification of colloidal solutions. So this we can be done by two methods, dialysis and ultrafiltration. When a colloidal solution is prepared, quite often it contains certain impurities of electrolytes which are crystalloidal in nature and tend to destabilize the solution. Hence, their removal is very essential. The following two methods are used for the purification of colloidal solution. First one is dialysis and second is ultrafiltration. The process of separating the particles of colloids from those of crystalloids by diffusion of the mixture through a placement or an animal membrane is known as dialysis. The separation of crystalloids from the colloids is based upon the principle that the particles of the crystalloids pass through parchment paper or cellophane membrane, whereas those of the colloids do not. The apparatus used is called a dialyzer and is shown in figure 7.5. A cellophane paper is turned into a bag with funnel tied in the mouth of the bag as shown in the figure for the addition of the impure salt. The impure salt is filled into the bag, which is then suspended into a vessel containing distilled water. After some time, whole of the crystalloid in solution passes out, leaving the colloid behind. The distilled water is renewed frequently to avoid accumulation of the crystallides, as otherwise they may start diffusing back into the bag. The above process can be quickened if an electric field is applied around the membrane. The process is then called the electrodialysis. Now note, the most important application of dialysis is in the purification of blood in the artificial kidney machine as shown in figure 7.6. The dialysis membrane permits small particles of the excess ions and waste product to pass through, whereas colloid sized particles such as hemoglobin do not pass through the membrane. Ultrafiltration is our second purification method of colloidal solutions. Ultrafiltration: ordinary filter paper is permeable to colloidal dispersions as well as to true solution and thus cannot be employed for filtering salts. However, a filter paper treated with colloidal or gelatin solution followed by hardening by dipping in formaldehyde solution serves the purpose. Due to this treatment, the pore size of the filter paper is reduced. Due to this treatment, the pore size of the filter paper is reduced. The filter paper so obtained is called ultrafilter, and the filtration device using such a filter paper is called ultrafiltration. By using the impregnating solution of different concentration, a series of graded ultrafilters can be obtained. With such ultrafilter, solute impurities of different sizes can be effectively removed. The salt is poured over the ultrafilter, which permits solution of electrolytes to pass through but retain the colloidal particles in the form of slime. Slime is in contact with water disperse spontaneously to form a colloidal system. Other filter media commonly used as unglazed, pore clean, and finally sintered glass. Since under ordinary conditions filtrations proceed very slowly, pressure or suction has to be applied to speed up the process. Now our next topic of this chapter is properties of colloidal solution. So our first one is on the basis of physical properties. So on the basis of physical properties we have four: heterogeneous characters, stability, filterability, and visibility. Colloidal, first one is heterogeneous character. So colloidal particles being larger than molecules form heterogeneous mixture consisting of particles of dispersed phase and dispersion medium. The phenomena of Tyndall effect, electrophoresis, and electroosmosis discussed later in this section confirm heterogeneity of colloidal systems. Now next is stability. So colloidal salts are quite stable. Only a few colloidal particles of comparatively larger size may settle but very slowly. Then next is our filterability. Ordinary filter paper cannot be used for removing the dispersed phase because size of pores of filter paper is bigger than the size of colloidal particles which can easily pass through the pores of the ordinary filter paper. Animal membrane or parchment paper does not allow the colloidal particles to pass through it. This forms the basis of separating the particles of the colloid from those of the crystalloids in the process called dialysis discussed earlier. Now, our last one is about visibility. Then the particles in colloidal solution are not visible in naked eye or under ordinary microscope. In fact, a particle is not visible if its size is less than half the wavelength of the light used to see it. Since the minimum wavelength of the visible light range is 3600 angstrom, therefore, with visible light, a particle of size less than 1800 angstrom cannot be seen, as the maximum size of the colloidal particles being less than 1800 angstrom, these are not visible. Then our second is colligative properties on the basis of osmotic pressure. Third one is kinetic properties on the basis of Brownian movement. Then we'll study about the causes of Brownian movement, then importance of Brownian movement. Fourth one is optical properties on the basis of Tyndall effect. Fifth one is our electrical properties, in which we have stability of colloidal sols, electrical charge on colloidal particles. Then in this only we have electrophoresis or cataphoresis. Then our electroosmosis, and last is our coagulation or flocculation. And in this only we'll study about the Hardy's schedule law. By our coagulation can also caused by the following methods: by electrophoresis, by mutual precipitation, by prolonged dialysis, by heating or cooling. Then our topic is protective action of leophilic colloids and gold number. It has already been explained that leophobic soil, like those of metals Au, Ag, etc., are unstable and are easily precipitated by certain leophilic colloids like gum, soap, gelatin, etc. Leophobic colloids like metal salt render leophobic colloids difficult to coagulate by the addition of electrolytes. The process is known as protection, and the leophilic colloids are termed as protective colloids. It is believed that the protective action of the leophilic colloids is due to the covering up of the particles of the leophobic colloid by those of the leophilic colloid. However, this explanation does not seem to be fully correct, because the particles of the protecting substance have almost the same size as those of the substances being protected. Thus, the exact mechanism of protection is not clear. To compare the protective action of different leophilic colloids, Zsigmondy in 1901 introduced the term called gold number. It is defined as gold number of the protective colloid is the minimum weight of its milligram, which must be added to 10 milliliter of a standard red gold salt containing 0.5 to 0.06 gram of gold per liter, so that no coagulation of the gold salt, that is the change of color from red to blue, take place when 1 ml of 10% sodium chloride solution is rapidly added to it. Evidently, smaller the gold number of the protective colloid, the greater is its protective action. The gold number of a few protective colloids are listed in table 7.6. Instead of gold number, the protective action of leophilic colloid is sometimes expressed in terms of Congo-Rubin number, as suggested by Oswald. It is defined as the minimum amount of the protective colloid in milligrams that prevents the color change of 100 ml of 0.01% Congo-Rubin dye, to which 0.16 gram equivalent of KCl is added. The reciprocals of gold numbers are included in the above table, as they give directly a comparison of the protective action. Now our last topic is emulsions. Emulsions definition: an emulsion is a colloidal dispersion in which both the dispersed phase and the dispersion medium are liquids. Now, method of preparation: an emulsion is prepared by shaking strongly the mixture of the two liquids, or by passing the mixture through a colloid mill called the homogeneer. The emulsion thus prepared from the pure liquid are usually not stable, and the two liquids prepared out on standing to get a stable emulsion. Small quantities of certain other substances are added during preparation. The substances added to stabilize the emulsions are called emulsifiers or emulsifying agents. The substances commonly used as emulsifying agents are soap of various kinds, long chain sulfonic acid or lyophilic colloids, proteins, gum, agar, etc. Role of emulsifier. The role of emulsifier can be explained taking the example of soap as an emulsifier. Soaps are sodium or potassium salts of higher fatty acids. Example sodium palmitate, sodium stearate, etc. A molecule of soap consists of two parts, the hydrocarbon part which is soluble in oil and the polar group which is soluble in water. R is our hydrophobic part which is soluble in oil. COO negative Na positive is hydrophilic part soluble in water. Thus, if a drop of oil is surrounded by soap solution, the R part of this soap remains in the oil and the COO negative Na positive part remains in water as shown in figure 7.3. 13. Thus, soap molecules are concentrated over the surface of the drop of oil. As a result, the interfacial tension between oil and water decreases, and hence they are intermixed into each other to form the emulsions, as we can see in figure 7.13. Now, next is your types of emulsions. If the term oil is used for any liquid which is immiscible with water and is capable of forming an emulsion with water, then the various type of emulsions may be classified into two types. These are emulsions of oil in water, which oil is the dispersed phase and water is the dispersion medium. Second one is emulsion of water in oil, in which water is the dispersed phase and oil is the dispersion medium. So evidently the type of emulsion depends upon the relative amount of the two liquids. If water is in excess, it is oil in water emulsions. If oil is in excess, it is water in oil emulsion. The type of emulsion formed also depends upon the nature of the emulsifying agent. For example, the presence of soluble soaps as the emulsifying agent generally favors the formation of emulsions of oil in water, whereas the presence of insoluble soaps containing non-alkali metal atoms favors the formation of emulsions of water in oil. Example of emulsions. The two well-known examples of emulsions are: first one is milk, in which the particles of the liquid fat are dispersed in water, and second one is cod liver oil emulsion, in which water is dispersed in the oil. To test the type of emulsion, the type to which the given emulsion belongs can be tested experimentally by any one of the following method. First one is microscopic method, second one is conductance method, and third one is by dye method. Properties of emulsions, which is our first one is emulsions exhibit all the properties like Tyndall effect, Brownian movement, electrophoresis, coagulation on addition of electrolytes containing multivalent positive ions as the dispersed particle, that is globules, are usually negatively charged as shown by colloidal salts. So, second is the size of the dispersed particles in emulsions is larger than those in the salts. It ranges from 1000 angstrom to 10,000 angstrom. Third one is emulsions can be broken to yield the constituent liquids by heating, centrifuging by adding larger amounts of the electrolytes to precipitate out the dispersed phase, or by chemical destruction of the emulsifying agent. The separation of cream from milk is well known example of centrifuging. Then the process of breaking an emulsion to yield the constituent liquid is called demulsification. Then our applications of emulsions are usual in a number of ways. A few of applications are given below. First one is in the metallurgical process. The concentration of ore by froth flotation process is based upon the treatment of the powdered ore with oil emulsion. The valuable particles of the ore form which comes to the surface and is skimmed off. Second is asphalt emulsified in water is used for building roads without the necessity of melting the asphalt. Third one is milk, which is an important constituent of our diet, is an emulsion of liquid fats in water. Then next is several oily drugs are prepared in the form of emulsions, and also the cleansing action of ordinary soap for washing clothes, crockery, etc. is based upon the formation of oily in water emulsion. Now, sixth one is digestion of fats in the intestines takes place by the process of emulsification. A small amount of the fat reacts with the alkaline solution present in the intestines to form sodium soap. This soap causes the emulsification of the rest of the fat, thereby making the function of the digestive enzymes easier in carrying out the metabolic process. Now, our last topic about emulsion is harmful effect of emulsions, and it is our last topic of chapter colloidal states. Harmful effects of emulsions are the formation of emulsions is sometimes harmful. For example, petroleum forms emulsion with water. Thus, in the petroleum wells, we get the emulsion sometimes instead of petroleum alone. Likewise, in the areas where small amount of petroleum are present, the well water becomes unit for use. Thank you. Uh, Thank you.